I'd like to spend a little bit of time talking about the exercises from the discrete probability worksheet. This is section 2.4. Now, I'm skipping some of the 2.4 material just because we were missing a week of class. And so we're going to skip exercise 7, but I'll go through the rest of them, and I'm hoping that's enough to get you guys started on the homework. Please keep in mind that if you have questions on the homework, you should read through the notes that I posted on Blackboard for section 2.4, but also you can always reach out to me. And if I can't help you through typing on email, then I'll make another video to go over specific homework problems. All right, so we're going to start with number 1 on the discrete probability exercises. And before we even get started, just as a quick review, remember that when we're trying to find the probability of some event E occurring, essentially what we're doing every time is we're counting out the number of ways that that event E could occur, and we're dividing it by the total possible number of outcomes. Okay, and so this probability, it should always be a number between 0 and 1, right? A fraction between 0 and 1. So, for number 1, I'm going to do it on a different piece of paper so I have some more space, but we're randomly selecting a number from 1 to 100, and we're finding the probability that various events could happen. So, first of all, let's think about what the total number of outcomes would be for each one of these, right? We're selecting some integer between 1 and 100, and so the total possible number of outcomes are, well, you could select 1 or 2 or 3 or 4 or 5, right? Any integer from 1 to 100. So the total possible outcomes is 100. All right, which means this is going to actually be our denominator in all of these, but maybe they'll reduce a little bit. Okay, so if we're trying to find the probability that the integer we selected is an odd integer, well, we just need to find the total number of odd integers between 1 and 100 divided by the total number of integers, that's 100. Okay, well, how many odd integers are there? We've done this sort of problem before, right? We're trying to count how many numbers are in this set. 1, 3, 5, 7, all the way up to 99. Okay, well, this is just, it's half of all the total number of integers. So it's 1 but not 2, 3 but not 4, all the way up to 99 but not 100. And so the cardinality of this set is 50. And so this probability is just going to be 50 over 100, which reduces to 1/2. Well, this makes perfect sense because half of the integers are even and half are odd, so the probability that you get an odd should be 1/2. Okay, using a similar method here, roughly 1/3 of the integers between 1 and 100 are divisible by 3, right? The numbers that are divisible by 3 would be 3, 6, 9, 12, all the way up to the last multiple of 3 before 100 would be 99. Right, these are our favorable outcomes here. These are the ones that are divisible by 3, so we just need to find the cardinality of this set. And one way to do that is if we divide every number in the set by 3, we're going to get a new set with the same cardinality. In particular, 3 divided by 3 is 1, 6 divided by 3 is 2, 9 divided by 3 is 3, all the way up to 33 divided by 3 is, 99 divided by 3 is 33. Now the cardinality of this set, of course, is just 33. It's all of the integers from 1 to 33. So in other words, if we're randomly selecting a number between 1 and 100, exactly 33 of those possible outcomes are divisible by 3, which means this probability should be 33 out of 100, which is basically 1/3, but it's not quite equal to 1/3, right? This is 33 is only divisible by 3 and 11. 100 is not divisible by 3 or 11, so this doesn't reduce. It's roughly equal to 1/3, but not exactly equal to 1/3. So the exact probability is 33 over 100. Okay, now for the last one, we want to find the probability that we select a number that's odd or a multiple of 3. This one's a little bit harder, right? Because you could try and say, well, there's 50 odd integers and there's 33 integers that are a multiple of 3, so maybe there's 50 plus 33, or 83 numbers that are one or the other. But of course, that's going to end up double counting some things, right? Because, for example, 3 is in both of these sets, 9 would be in both of these sets. We don't want to count those twice, so it's not as simple as just adding 50 plus 33. Okay, so how do we count the number of numbers that are odd or a multiple of 3? It's an OR statement, so it's like the addition principle, but there's overlap, which means we need to use principle of inclusion-exclusion to count how many numbers are odd or a multiple of 3. Okay, so how many are odd? We've done that already. We know that there's 50 numbers between 1 and 100 that are odd. Now we add to that, how many are multiples of 3? Right, well, we did that up in part B. There's 33 of them. Now we're going to subtract, right? Principle of inclusion-exclusion says we subtract the ones that have been double counted, the ones that are both odd and a multiple of 3. Okay, how many of those are there? Well, let's think about which ones they would be, right? So we could say, look at this set of the multiples of 3. We only want the odd ones. We want 3, we want 9, we want 15, that's the next one in line, all the way up to 99. So it's just about half of them, except there's 33 total, so half is, well, it's 16 and a half. That's not a whole number. It needs to be a whole number. And so do we round up or do we round down? Well, we're including the first and the last in the list, so we would round up. Okay, so it'd be 17 that are odd and a multiple of 3. If you didn't follow that, you could just list them all, right? They'd be 3, 9, 15, 21, 20, 7, right? It wouldn't take too long to actually list all the numbers that are odd multiples of 3 up to 99. And you can convince yourself, hopefully, that there's 17 of them altogether. Okay. And so principle of inclusion-exclusion says take the number that are odd plus the number that are multiple of 3 and then subtract the ones that are both. So altogether, this gives us, let's see, 83 minus 17, which would be 83, 73, 64 altogether. Okay. So there's 64 numbers that are favorable outcomes for us, that are either odd or a multiple of 3, which means this probability is going to be 64 over 100. Okay, and this reduces, they're both divisible by 4, so 16 over 25. Okay, right, so that's number 1. Number 2, what is the probability that a normal coin lands heads up 6 times in a row? So we're assuming here that we're flipping a normal coin exactly 6 times in a row, and we want to know the probability that it lands heads up all 6 times. All right, so first we find the total number of outcomes. So each time you flip it, it's either going to be heads or tails, right? Heads or tails, all the way down the line. So there's 2 outcomes every possible time. So when you flip a coin 6 times, the total number of outcomes is 2 to the 6th. That's our denominator. Right, so the probability that you get all heads is the number of favorable outcomes divided by the total number of outcomes, which is 2 to the 6th. Well, the only favorable outcome here is if we definitely flipped heads the first time, and we definitely flipped heads the second time, and the third, and the fourth, all the way down the line. So there's only one outcome that we're looking for. It's the outcome where you actually flipped heads every single time. So this probability would be 1 over 2 to the 6th, or 1 over 64. All right. Now this next one's similar. It's saying you're flipping a coin 10 times in a row. What's the probability that you get exactly 5 heads, given that the first 3 flips came up tails? Okay, now this one's a little bit different. You might think the total number of outcomes here is 2 to the 10, the same way that the number of outcomes in our last example was 2 to the 6. But they're telling you some extra information here. They're telling you that the first 3 flips came up tails. So if we think about all the different outcomes when we flip a coin 10 times, 5, 6, 7, 8, 9, 10 times, and they're telling us the first 3 flips were definitely tails. So we don't have 2 options for each of these because we already know that they're tails. We only have 1 option for each of these. And so for the remaining 1, 2, 3, 4, 5, 6, 7 spots, there's 2 options each time, heads or tails. And so the total number of outcomes here is 2 to the 7. Okay. Now we want to know, in this scenario where your first 3 flips were tails, what's the probability that you got altogether a total of 5 heads? Right? Meaning out of these last 7 flips, what's the probability that 5 of them were heads? Okay, so we need to find how many sequences of 7 coin flips have exactly 5 heads. And if you think back to before spring break, these many weeks ago, we actually had a similar problem on the warm-up here, right? There's 7 spots to fill and we're trying to figure out how many sequences have exactly 5 heads, and so that means we would have to have exactly 2 tails. Well, out of those 7 spots, we would need to choose 5 of them to be heads or choose 2 of them to be tails. And so there's 7 choose 5 or 7 choose 2, they're equal. It's 7 factorial over 5 factorial times 2 factorial, such sequences. So this probability is going to end up being equal to the total number of favorable outcomes that we found down here, 7 factorial over 5 factorial times 2 factorial, divided by the total number of outcomes, 2 to the 7th. That's our probability. Or if you wanted to, you could rewrite this, moving this 2 to the 7 into this denominator as 7 factorial over 5 factorial times 2 factorial times 2 to the 7. That works as well. Okay, this movie's getting a little long. I'm going to do a different video for the last few problems.